contamination and overheating. Basic idea of condition monitoring is to take action before any catastrophic failure starts. So there are points where the potential failure starts, and if it is attended to at that moment, the catastrophic failure can be avoided. Next slide, please. For example, dielectric insulation failure. Dielectric insulation failure is basically can be tested on a regular basis. Several type of tests from the winding insulation resistance test, tan delta test, capacitance test, etc. They can be done to make sure that the insulation is parameters are maintained properly. And if those parameters are deteriorating, then what action to take at what time, within what time frame. Because always there is a gap between the potential failure and actual failure. This is called as per the PF curve. So there are several type of condition monitoring diagnostic tests: core insulation resistance test, binding resistance test, insulation test, SFRA. SFRA is a test which tells about the winding conditions and the core conditions. Then there are other type of tests. Change, please. For example, there is a winding failure indication here. This is the type of failure that we need to avoid. So coming back to the transformer, basically the basic principles are important to understand. I'm sure all of you are familiar with these, but still let us go through it. The basic principle is primary voltage in the winding sets up electromagnetic flux in the core. Primary could be on the low voltage side, primary could be on the high voltage side. So any winding can be primary, except that we call the primary that winding on which the supply is provided, and the other winding which is secondary winding. Sometimes there is a tertiary winding also, so that there can be one primary and two secondary. So one of the secondary becomes a tertiary winding. So this flux cuts into the secondary winding and induces a voltage in the secondary winding. The induced flux of the secondary winding voltage depends upon the number of turns. So one basic parameter of any transformer design is volts per turn. So this is the way it looks like in a core. There are two coils here, and it sets up a flux due to high admittance of the magnetic core, or very low reluctance of the magnetic core. Most of the flux remains inside the core, and this travels along the core and links with all the windings of the core. Next, please. So this is the basic design equation of any transformer, and the voltage value is in RMS. E is equal to 4.44 F N A B max, where E is the winding in volts, F is the operational frequency, N is the number of turn, A is the area of cross section of the core in meter square, and B max is the maximum flux density Weber per meter square. The B max is a quality of the magnetic steel. So nowadays 1.7 to 1.8 Weber per meter square quality materials are available. Earlier, the CRGO or other type of material were there which had lower flux density. Nowadays, better quality material are available, so transformers cross-sectional area can be reduced for same kVA rating, and therefore the transformer can be made much more smaller, low losses, and more efficient. Next, please. So some of these specifications are written on your transformer nameplate. For example, kVA, phases, voltage ratio, frequency, cooling, vector group, impedance, weight of core, coil, tank, fitting, etc. So these are the important specifications, and they should be properly noted, recorded, and understood. Next, please. So question is, many times people have asked me what is a vector group and what does it mean and how it is represented and what is the implication of the vector group. So I would like to dwell a little bit upon the vector group. You must have seen on the vector group written as dy11n or something like that. Next, please. Vector group basically means that